Hello everyone, this is Chenning from Zhejiang University. Today I would like to introduce our work, C for Contrastive Cross-Language Code Clone Detection. In recent years, cross-language clone detection have attracted attention from researchers. Cross-language clones are caused by different platforms and programming languages. Developers have to develop the same functionality programs written in different programming languages for different platforms, such as apps in C or C# for Windows PC, Swift or Objective-C for Apple platform, Java for an Android phone. Different from traditional clones, cross-language clones are created intentionally by developers and are often unavoidable and cannot be removed. Detecting cross-language clone automatically is helpful for developers to manage cross-language software system in an easy, time-effective, and cost-effective way. Compared to a single language clone detection, cross-language clone detection is much more difficult. There are mainly two challenges. First, the programs are heterogeneous. It is hard for static analysis tools to illustrate different internal mechanisms and characteristics in programs. As the example shown above, C++ solution use vector while Python's solution use NumPy. Though deep learning-based approaches are effective in mapping code snippets into a high-dimensional vector space, many existing deep learning approaches are proposed to detect single-language code clones. Distinguish clone or non-clone pairs is another challenge. Existing studies usually measure the vector distance to detect clone pairs. However, two code fragments have identical functionality but different in lexical or syntax may not be recognized as similar by existing models. Likewise, these models cannot distinguish between two code fragments that differ in functionalities but share a close syntax resemblance. To address the above issues, we propose a new approach named C4 that exploits the pre-trained model CodeBERT with a contrastive learning objective. The overall framework is illustrated by this figure. We process all programs into batches, where each batch consists of code snippets that belong to the same task but use different programming languages. For each code snippet, we exploit the CodeBERT to get its representation. Then we use contrastive learning for every code snippet in the batch. To address challenge 1, we use CodeBERT as our pre-trained model since it's trained on multiple programming languages. The first step is data process. We process all programs into batches, where each batch consists of code snippets that belong to the same task but use different programming languages. For each code snippet, it is first split into a list of words. Then it is put in the CodeBERT's tokenizer. The second step is to get code representation. We feed the code into the model, and it will generate a vector representation shown in the figure. We only use CLS for code clone detection because it is the sentence representation. We fine-tune the model use contrastive learning, which will be illustrated in the next slide. The loss function for contrastive learning is shown in the slides. Tau is a hyperparameter that we tune to scale the penalties of negative samples. As shown in figure, C4 exploits the contrastive learning to learn effective representation by pulling clones together and pushing apart non-clones. The detailed algorithm of how to compute loss is shown in algorithm 1. For each batch we process, assume the batch size is B. It means that we have B clone pairs in this batch. We then loop over the batch. For each pair, we take the first one as an anchor example, the second one as a positive example. Ideally, the rest clone pairs will be negative samples. Thus, the number of negative examples will be 2 multiplied b minus 1. However, the rest of programs may come from the same problem. We should filter out these code snippets. After constructing positive examples and negative examples, we compute their cosine similarity with the anchor example. The dataset we use was constructed on Google's CodeGem and AT Coder. For C4, we only need clone pairs, so we get these examples. For CLC-DSA and CLC-Miner, we follow the experiment setup of CLC-DSA and randomly select from different programs to create non-clone pairs for one clone pair. The statistic for the language code blocks can also be seen in the slides. We compare our approach with two state-of-art approaches, CLC Miner and CLC DSA, and we can see from the table we outperforms the baseline a lot. We can see the specific language pair clone detection result in table, and we can find that all evaluation matrix in our approach is better than CLC Miner. Our approach's precision outperforms CLC DSA a lot, and the variance of our approach is very small. We investigate the impact of variance on the performance of our approach. We compare our approach with two of its incomplete variants, CodeBERT without fine-tune. We directly use the pre-trained CodeBERT to detect cross-language clone pairs without fine-tune and contrastive learning. And CodeBERT with fine-tune, we fine-tune the CodeBERT without contrastive learning. During the fine-tune process, we use MIC as our loss function, and that is used in the original CodeBERT. Table show that without fine-tune, the model regards all pairs as clone pairs, and contrastive learning can improve precision score very much. We visualize the code vectors to help understand and explain why the vectors produced by C4 are better than the vectors produced by others. As shown in the figure, points in the same color represent programs from the same problems. We can easily see that contrastive learning can keep dissimilar pairs away while pulling similar pairs together. Considering the long training time for C4 and CodeBERT, we further conduct an experiment on smaller dataset that is more energy efficient. We find that C4 small has the same performance as C4. However, the performance of the fine-tuned CodeBERT has an obvious decline. That's all. Thanks for listening.